Aliens. We often think of them as creatures not of this world, but what if they are closer than we think, and in our own oceans? Cephalopods have long been seen as otherworldly or mythical, with stories of the Kraken sinking ships dating back to 1180 AD, showcasing how these often large marine mollusks, related to something as simple as a snail, influenced historical societies. Today the octopus, a soft-bodied cephalopod of order Octopoda, is regarded as one of the smartest, most cunning invertebrates that is found in every ocean. From dynamic intertidal pools to the hidden depths of perceived sanctuaries that conceal intense challenges. Females of these semiparous invertebrates reproduce once and then die, so adaptations to extreme environments is essential. Testing is endurance and physiology at the extremes. The rocky shores of Western Australia. Here, life thrives in the face of human activity, relentless waves, and dynamic tides. Rock pools exposed by low tides become battlegrounds for soft, nutritious invertebrates like the octopus, as they endure the scorching sun followed by fluctuating salinities, all under the watchful eye of predators. Not just its egret at low tide, but other gull species, and the ultimate predators in proximity of these rocky shores, humans. Abdopus aculeatus, or the algae octopus, is a resident of these intertidal rock pools. Named after its stationary mimicry of an algae-covered sea snail shell, they only live for about 1 or 2 years. Overnight, it shelters in dens, blocking the entrance with pebbles or shells as a display of its tool-using intelligence. But the rising sun causes the algae octopus to leave its den in search of a meal. Like most octopus species when hunting, it must blend into its surroundings to avoid alerting prey and predators. To do this, specialized skin components called chromatophores have muscles that, when contracted, open pigment sacs, causing a color change. And despite their colorblindness, this detailed crypsis is also down to their other pigment cells, iridophores. These cells reflect light to enhance its mimicry. Now camouflaged, it walks slowly on 2 arms, using the remaining arms to mimic luscious marine vegetation. The algae octopus has a unique skill. It waits, peering its eyes just above the water, and then it emerges. They are one of the few cephalopods that regularly move on land and scale rocky shore terrains. Almost moving like jelly across a landscape, it searches for food or better rock pool conditions. It uses its biserial double-rowed suckers to crawl across the terrain to find a new pool. Navigating new territory can be challenging. Usually, sensitive cirrifilaments on the arms help with navigation. However, the algae octopus lacks these filaments and must rely on its remarkable brain power. 2/3 of its neurons are located in its arms, each acting like a mini brain that gathers substantial sensory information on its environment to drive arm movements without using major brain regions. Spending extended periods on land means they must maintain oxygen levels without relying solely on their gills. With a mantle or head size of up to 7 centimeters and slender arms that can reach 25 centimeters in length, the algae octopus has an ideal body for cutaneous respiration. This is where the oxygen and carbon dioxide are exchanged through the wet skin. all thanks to the high surface area to volume ratio of its physiology. Using its developed vertebrate-like eyes, and by moving between rock pools, the octopus targets unsuspecting swimmer crabs. Its hard beak would pierce the chitin exoskeleton, while gripping its dinner tightly with its 8 sucker-lined arms. Survival in rock pools isn't just about food, it's also about oxygen. At night, when photosynthesis halts and oxygen drops, the octopus thrives thanks to its blue blood, rich in copper-containing hemocyanin that binds 24 times more oxygen than human blood, allowing it to thrive in low-oxygen environments. As the day comes to a close, the octopus must quickly return to its den. It draws water into its mantle head region and expels it through its siphon. This jet propulsion generates enough speed for the octopus to quickly retreat into hiding if it's threatened, ensuring it survives to see another day of the rocky intertidal zone. Beneath the vast expanse of the North Pacific Ocean lies a world few have seen. Here, deep-sea expeditions that use remote-operated vehicles, or ROVs, are deployed to the depths. These mechanical explorers are the eyes and hands of scientists. Using cameras, and sampling arms to investigate geological features and the vast biodiversity, unveiling the secrets of the deep. Ocean Networks Canada, owned by the University of Victoria, collects data from Canada's Arctic, Pacific and Atlantic coasts. Through their database, Oceans 3.0, and collaborations with ROV operators like the National Oceanic and Atmospheric Administration and Fisheries and Oceans Canada, they've built Seatube, a deep-sea video archive publicly available worldwide. Now we dive deep into this vast resource to explore some species of octopus that inhabit the deep.
Wow.
Yeah, that's pretty amazing, hey?
She's totally posing for us.
Wow, a really steep rock feature underneath of us right now.
The bathypelagic zone, 1,000 to 4,000 meters below sea level, is where the ocean becomes a realm of extremes. Constant darkness, high pressures, cold temperatures, a lack of light-dependent phytoplankton, as well as fewer zooplankton to sustain the food chain, makes survival at these extreme depths a constant challenge. Yet life thrives. This midnight zone hosts vast coral gardens that form towering structures from a steady rain of organic debris nutrition from the surface. Deep-sea skates patrol the ocean depths, resembling rays that give birth to live young. But unlike their relatives, skates lay eggs encased in tough, leathery sacs known as mermaids' purses. King crabs can be found reproducing and hunting in the cold depths, while predatory sea stars, tube worms, and many other invertebrates colonize deep-sea structures alongside intelligent cephalopods, all adapted to survive the midnight zone. Octopus of the midnight zone are uniquely adapted to this low-energy environment, with their existence depending on efficiency in everything they do. Unlike their shallow water relatives, and to counteract these nutrient-scarce, hostile conditions, deep-sea octopus species have evolved longer lifespans and extended brooding periods to ensure egg survival. Efficient movement is vital for conserving energy in the deep sea. The Muusoctopus genus, a group of octopus that lacks an ink sac, relies on precision movement to navigate the deep. A slight burst of jet propulsion sends it forward, It then extends its webbed arms, using its interbrachial membrane between tentacles to glide with the currents. This webbing can also trap unsuspecting prey near its mouth, showcasing how every motion is calculated so every ounce of energy can be conserved. Successful reproduction at depth is also essential for thriving populations of deep-sea octopus. Graneledone Boreospecifica, or the deep-sea octopus, the most abundant deep-living octopus in the eastern North Pacific, is an unexpected world record holder. Females lay eggs, caring for them throughout the brooding period, which for the deep-sea octopus lasts an astounding 4.5 years, the longest known in the animal kingdom. Lower environmental temperatures mean lower metabolic activity, possibly leading to a prolonged brooding period in marine ectotherms like the deep-sea octopus. Experts therefore speculate that the species may live up to 18 years, as the brooding period typically accounts for a third of an octopod's lifespan.
Look like little boots. All
Yeah,
curled out.
it is. But it makes so much sense if you were just walking on your tippy toes in this, we would just sink right into it, right?
Totally.
Before brooding, the deep-sea octopus often walks along the soft sea floor, curling the tips of its arms to avoid sinking into the silt. With a dense concentration of sensory neurons in their arms, they feel for prey beneath the surface, and when a target is found, they uncurl an arm in a flash to capture it. And when the time comes, the mother expertly cements her eggs to rocky outcrops, using her siphons and water currents to oxygenate them, while vigilantly covering them 24/7 for protection. A long brooding period under constant protection means the hatchlings emerge highly developed, ready to swim and hunt immediately, significantly boosting their chances of survival. This species therefore adopts a K-selection reproductive strategy, categorized by investing a lot of time into nurturing and protecting eggs, while often producing fewer offspring. As the developing young grow within their eggs, their large eyes are visible through the chorion, a remarkably thin membrane that facilitates oxygen diffusion. The female's arms are then used to defend the eggs from potential predators by curling them upwards, ready to fend off attackers. King crabs. These large crustaceans of the deep are opportunistic hunters that prey on vulnerable females and their eggs. Surrounding the deteriorating female, they try to snatch the eggs. Remarkably, the female is able to fend them off with her arms. As her strength fades, her body will appear pale, smaller and swollen, leaving the king crabs to wait until she dies at the end of the brooding period.
These crabs must sense that, like the timing is coming to a close now.
Yeah, because they are scavengers.
The dedication of the female Graneledone Boreospecifica to her young exemplifies the intricate balance of survival and adaptation in the deep sea. She even refuses food, starving herself over the 53-month period, becoming increasingly pale, all to ensure her offspring survive and carry her genetic legacy into the next generation.
Might be at the end because she's so pale, they don't move, they don't feed, they just take care of their babies the entire time, so it's kind of crazy. And then they die. Actually, they don't really know what happens to the males, but they suspect they die too after mating.
At the boundaries of tectonic plates and along ocean ridges lie the ocean's hot springs, hydrothermal vents. Seawater seeps through deep fissures, heated by magma beneath the crust, and under immense pressure, minerals dissolve into the superheated water, which can reach over 370 degrees Celsius. As this hot water mixes with the freezing deep sea, the minerals solidify, forming towering vents. These vents come in two forms: tall, black smokers rich in sulfides, and smaller, white smokers filled with calcium, barium, and silicon.
If Dr. Ballard was the first to discover hydrothermal vents, and the attribution is given to Dr. Ballard and a team of 30 marine geologists, geochemists, and geophysics who discovered hydrothermal vents on the ocean floor near the Galapagos Islands in 1977.
Unexpectedly, life thrives at hydrothermal vents. Seawater rapidly cools expelled water to around 20 degrees Celsius, creating an ideal environment for various species. Sunlight, the source of energy for most of Earth's biodiversity, is completely absent in the midnight zone, but this is no barrier. Bacteria harness the chemically enriched waters to perform chemosynthesis, generating vital nutrients. These bacteria either live in symbiosis with invertebrates, or are eaten by scavengers and filter feeders. This process sustains a vast food chain, making vent ecosystems one of the largest communities on Earth that has adapted to the darkness.
Yes, we are working with BBC for a potential upcoming documentary about deep sea environments, and so when we get the kind of what we're calling mood lighting going, we're considering shots for them, and of course they love charismatic ones like this gorgeous octopus.
Sustained by a chemosynthetic food chain, the vent octopus, Vulcanoctopus Hydrothermalis, is the only described cephalopod that calls hydrothermal vents home. This small species can tolerate temperatures up to 91 degrees Celsius, preying on unsuspecting crustaceans like crabs and small amphipods, as well as thriving tube worms that cling to basaltic vent cliffs. Higher currents and unstable sediment around hydrothermal vents mean that the vent octopus must use its 2 rows of suckers on each arm to have a secure grip, while its front dorsal arms explore and the ventral back arms propel it forward. In the total darkness of its habitat, it has evolved without defense mechanisms like chromatophores or an ink sac, making it appear semi-translucent, a true ghost of the deep, resembling other deep octopods like the glass octopus. As masters of adaptation, these octopus have conquered some of the world's harshest habitats, thriving where few can survive. In an environment as vast and mysterious as the ocean, unexpected ecological interactions flourish, prompting us to wonder how other vertebrates and invertebrates have evolved to endure such extremes.